from University of Graz, and he will talk about derived categories of singular varieties. So please.
Okay, thank you very much, Pedro, for the introduction and for the invitation. It's a great pleasure to speak here. Yeah, so please interrupt me at any point. I might not be able to kind of see raised hands. Please just speak up if there's any questions. So yeah, I want to talk about kind of the derived categories are mostly in the background, actually, at least yeah, in the beginning of the talk, maybe for most of the time, depending how fast I am. So I want to start with some introduction motivation. And so I have drawn a picture here. So here you can see a tree. In this tree, it's kind of like a binary tree, except for at the very top. It goes on infinitely to the bottom. At each vertex, we have triples of integers, positive integers. It starts with 1, 1, 1, then comes 1, 1, 2, and so on. And I imagine some of you might have seen this tree before. It has a name. This is known as the so-called Markov tree. And now I want to tell you how these numbers come about, what the meaning of these numbers are, or what the meaning of these numbers is. And then I want to explain how, I mean, why I care about this and how this is related to some questions in algebraic geometry. So now here comes another board. This is the theorem due to Markov almost 150 years ago. And it says that if we look at this Diophantine equation, x squared plus y squared plus z squared equals 3 times xyz, this is known as the Markov equation, then all positive integer solutions of this equation can be obtained from the kind of almost obvious solution, 1, 1, 1, by iterating two operations. First operation is permuting the elements in the solution. This equation is completely symmetric. So if we permute the elements, we will still get a solution. And then the second operation is called mutation. There we replace one entry by the formula 3 times the other two, the product of the other two entries minus the entry that we want to replace. And this operation is known as mutation. And so all the solutions can be obtained in this way, and these solutions are known as Markov triples. And so, I mean, it's a bit unfortunate with these blackboards here, but maybe in this tree, we can see, for example, that going from this 1 to 5 to here, well, we first permute so that the 2 and the 5 are in the beginning, and then we apply this formula saying that we have to take 3 times 2 times 5, which is 30, minus 1, so that's the 29 here. And so this is how all these solutions are obtained. Yeah, and so actually, yeah, this turns out that this equation and these solutions turn up in many different places in mathematics. And we are going to look at 2 such instances today. So the goal for the start is to relate this Markov tree, which is on the blackboard behind, to certain triples of reflexive sheaves, F1 up to F3. So we would, instead of having a triple of positive integers, we then have triples of such reflexive sheaves in our tree on singular projective surfaces. So the smooth surface that we are going to look at is just the projective plane P2. And on there, these F1 up to F3 will be vector bundles. And on the singular surfaces, they will almost be vector bundles, very close. And one of them actually will be a vector bundle. And so this follows work of many people, which I've listed here. So now I'm going to give some definitions that I think are needed in order for me to state the results that kind of answer this goal to some extent. Okay, so now I'm starting to actually write on the blackboard. Let's see. Okay, so I want to start with explaining what exceptional sheaves and exceptional sequences are. So the setting is that X is a projective variety over complex numbers. And now the definition of an exceptional object. So for simplicity, I will talk about sheaves, at least in the beginning, and this is all the objects that will appear in our examples later will be sheaves, but you can also define all of this more generally inside the corresponding bounded derived category of coherent sheaves on X. So such a sheaf is called exceptional. Essentially, if its graded endomorphism ring is very exceptional, minimal in the following sense. So first of all, we can look at the endomorphisms. They should be as small as possible. They should just be scalar multiples of the identity. And then we also have potential for extensions. Since we have a sheaf, these extensions will all be positive, if there are any. And what we require is that there are none. All positive extension vanish. And so these two conditions together means that the graded endomorphism ring, the endomorphism ring of this object inside the derived category is minimal. And so this is certainly an exceptional property, and in most varieties, we might not even have such objects. For example, if we have a Calabi-Yau variety, then Serre duality prevents this from happening. As soon as we have a non-zero object, we will also get some extensions. Okay, but there are luckily examples where this works, and for us, the most important example will be line bundles O twisted by I on X being projective n space. These are exceptional. And so this follows, since one can check quite easily that the structure sheaf is exceptional, and then applying an autoequivalence, in this case tensoring with such a line bundle, preserves this property of being exceptional. And if we restrict to P2, which we will do later, then it turns out that all exceptional sheaves are actually slope-stable vector bundles by work of Dresé and Leportier from the mid-80s. And so now, having such exceptional sheaves or exceptional objects, complexes here in the derived category. I mean, I should say that if we look at objects in here, we need to change this condition here. We need to kind of say that all non-zero extensions are zero and vanish. Okay, so this is the definition of exceptional objects. And now we can form a whole collection of them. And we require some direction of the graded endomorphisms as follows. So part B of this definition is an exceptional sequence E1 up to ET of exceptional or yeah, I mean these EI are exceptional objects such that we have X only from sorry, they're called E. We are only allowing X going in this direction from smaller to larger values. So in other words, we require this to be zero if J is strictly greater than I. Okay. And here's an example. O, O1, so on up till On. This is an exceptional sequence on projective n space. And if we would add any more line bundle here, go up to On plus 1, then Serre duality would tell us that this is not exceptional anymore. Okay. So such an exceptional sequence is called full exceptional sequence if it generates the bounded derived category of coherent sheaves on X. What does that mean? Well, roughly that means that so objects in here are bounded complexes of coherent sheaves. And so if such a collection generates, that means that I mean, say if it's just sheaves, these E1 up to ET, then that roughly means every bounded complexes of sheaves on X is quasi-isomorphic to a complex C where all Ci are isomorphic to direct sums of shifts of these elements in our sequence with some multiplicities Mj, something like this. Yeah, so in other words, every object in our derived category can be produced from these by taking iterated cones and shifts. Yeah. Okay. So this is the notion of an exceptional an exceptional sequence. And why do people care about this? So let me clear the blackboard. So one can think of these exceptional sequences as basis of the derived category, as one would think of a basis of a vector space or of a free module. And there's a way of making this precise. Which I will write down a moment. Okay. So, there was an example missing here, sorry. This you can still see, good. So for example, the sequence that maybe I just put it here, sorry. So this sequence, this is full. O1 up to ON is a full exceptional sequence on Pn. This follows from the Kosul complex. Okay, so then I can continue here with the remark. If E1 up to En is a full exceptional sequence, then I can look at the classes of these EI in the Grothendieck group of X, which, well, let's say, I mean, if I have a full exceptional sequence, then actually, and X say has only Gorenstein singularities, it already follows that X is smooth. So K0X is kind of, it doesn't really matter how I define it. Say I define it as K0 of the category of vector bundles on X. So that would be kind of the traditional way, but this is also the same as K0 of the bounded derived category of X in this case. So this uses X smooth. Okay, so what's the statement? If we have such a full exceptional sequence, then these classes in the Grothendieck group form a semi-orthonormal basis of the Grothendieck group. So the Grothendieck group, in this case, is a free abelian group of finite rank, and the rank is exactly this n, and these classes are one basis. Yeah, maybe I should say here Z basis. Okay. So yeah. Now there's another remark, and this remark gets us closer to stating the relation with the Markov tree. So maybe now I need to swap the blackboards. So if we have, we are lucky enough to have found such a full exceptional sequence, or some exceptional sequence, not necessarily full, we would like to be able to produce more exceptional sequences. And this can be done. So this is the following remark. And it says, given an exceptional sequence E1 up to En, there exists new exceptional sequences of the following. So there's one where we go here up to EI minus 1. Then here we would have EI usually, but now we replace it by something that is called the mutation of EI plus 1 across EI, the left mutation. This is what this L stands for. Here we would have EI. Here we would have EI. Now, usually we would have EI plus 1, but this was moved here before EI. So that we leave out now, and we continue with EI plus 2 and go up to En. So this is known as the left mutation. Or a left mutation, because we can do this at any point of our sequence. And then there's a dual notion of a right mutation. And so that takes E1 up to EI minus 2. And then we would have EI minus 1 here, but this is moved to the right. So we continue with EI. And here we have the right mutation over EI of EI minus 1 and continue with EI plus 1 and now all the way up to En. Okay, so given an exceptional sequence, we have produced 2 new sequences, and the statement is that they are also exceptional sequences. Okay. It's not really so helpful, I think, to tell you how they look like exactly. I mean, that's something you can look up. But what's important for us is these sequences are full if and only if the original sequence is full. So this property of generating the derived category is preserved by these mutations. There's one remark that I forgot to mention up here. So one might wonder whether the converse implication up here also holds. Assume that, assume we have an exceptional sequence, but we don't know whether it's full or not. And assume that we know that the classes of the elements in the sequence form a Z basis of the Grothendieck group. Then one might wonder whether the sequence is already full. Unfortunately, this turns out to be quite wrong. And this is related to this notion of so-called phantom categories. So there are examples of exceptional sequences which form Z bases of the Grothendieck group, but they don't generate the corresponding derived category. Yeah, that's kind of a bit annoying and tricky to get one's head around, because then like looking at classes in the Grothendieck group is a very nice way of attaching invariance to objects in our derived category. And so in this phantom part, we don't have that tool at our disposal, unfortunately. Okay, so that was a remark about this. And then, yeah. Exactly. So now I want to comment on the case of P2. So on P2, if we are starting with an exceptional sequence, this has lengths 3, E1, E2, E3 of vector bundles, then mutation will preserve this, or sorry, this is actually a full exceptional sequence, but it doesn't really matter. You start with the full exceptional sequence of vector bundles, then any kind of mutation will again be a sequence of vector bundles, and it will be full by this remark. So we don't leave the world of vector bundles. So mutation will again be sequences of vector bundles. Okay, that's also a remark. And here's an example so that, yeah, we have something to illustrate this. Look at the sequence O. So which sequence did I want to take? So O minus 2 up to O. These blackboards have a life of their own, unfortunately. O minus 1, O. So that if I mutate O across this one, so I mutated here, left mutation along this one, then, so here I put left O minus 1 of O, I get O minus 2, and then the cotangent sheaf omega 1, and here I get O. And so if we look at the ranks of the vector bundles in these sequences, here these are all line bundles. So we have 1, 1, 1. And here we have line bundles here and here. And this one has rank 2. Okay, and now looking back at this Markov tree, we see that both triples actually appear in this Markov tree, and it turns out that this is not, well, I mean, sorry, this one here does not appear directly. This one only appears after permutations. But here we chose one representative for every triple under the action of the permutation. Yeah. Okay, so this is not a coincidence that these two triples of ranks of the vector bundles in a full exceptional sequence on P2 give us solutions of the Markov equation. This is a result due to Gorodentsev and Rudakov, which I'm going to write down in a moment. Okay. Yeah, I'm afraid there's not enough space there to write it down there. So clean this board here. Or maybe, yeah. Okay. Is everything readable so far? Yeah. Okay.
Yes. Could I ask a question? So
Yes,
is it-
sure.
is it possible to write down what the mutation does on the lattice K0?
Sorry, say it again, please.
Is it possible to write down what the mutation does on the lattice K0? So in terms of chain character.
Ah, yes, 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 yeah. So that involves the Euler pairing on the Grothendieck group. So we've got this Euler bilinear form, and so using that you can write down what the mutation does on the Grothendieck group. So is the question that you want me to do it, or is the question whether it's possible to do it?
Or other easy example that we can see how the mutation. Yeah, for instance, for this P2 example, is it possible to write down?
In the P2 example, in the P2 example, well, you need to, I mean, in principle, in any example, what you need to do, I hope I get the direction right. So let chi, say of so F and G are objects in the derived category now. And so now define the Euler form as the sum over the k dimensions of the Hom spaces X from F to G shifted by I. So this would be the Euler form.
You take the alternative sum.
Yes, thank you very much, of course. This, and now the mutation, so let's say we take the left mutation, the class of the left mutation, and here we have EI plus 1. So this should be, you take the Euler pairing from EI to EI plus 1 times, so this is now an integer, right? So you can multiply it with the class of EI, and then you subtract the class of EI plus 1. If I'm not mistaken, then this should be the way to write it down. Is that okay?
Oh, thank you.
Okay, so now let me state the theorem of Gorodentsev and Rudakov. which I think is very beautiful. So it says that every full exceptional sequence E1, E2, E3 of vector bundles on P2 is an iterated mutation. So meaning you allow all these left mutations and right mutations at any place where you want, of a sequence O twisted by 1, O twisted by 2. So this is the first part. So in other words, all full exceptional sequences of vector bundles on P2 are understood once we understand this mutation operation in detail. And the really beautiful thing is that on the level of the ranks of the vector bundles in my sequence, mutation of the sequence corresponds to mutation of the corresponding Markov triple. So the second part of the statement is that, moreover, the ranks Ri rank of EI form a Markov triple R1, R2, R3. And every Markov triple arises in this way. Okay, and the key point of the proof is actually the second part. They first show that if one has a full exceptional sequence of vector bundles, then the ranks satisfy the Markov equation. So then we are located somewhere. We are located somewhere in this Markov tree in terms of the ranks. And then in the Markov tree, we know which mutations to apply to go backwards to the very top. And then we do the same mutations on the level of exceptional sequences. And we will arrive at a sequence of line bundles. And then such a sequence of line bundles can always be mutated to this sequence. One can show that. So this is kind of the idea of the proof, and the really the harder part is to show that the ranks satisfy this Markov equation that uses Riemann-Roch theorem. Okay, so this is one way that the Markov tree shows up in algebraic geometry, and now I want to present another way in which it shows up, and then try to explain how these two ways are related. So the next part is about degenerations of P2. So again, P2 is involved. Okay, so what we want to do is we want to study flat proper analytic families of surfaces. So this is the total space of this family. And this should be over some small disk. So something like this. And how does P2 come in to play? It should be such that the special fiber over 0, which for later use I denote V0, is a singular surface. This is why it's called degeneration. And if T is different from 0, then the general fiber should be isomorphic to P2. And here I mean singular projective surface. Okay, and so this is, depending on your viewpoint, this is a degeneration of P2, or if your main interest is the singular surface, then people would call it a smoothing of this surface to P2. So degenerations of P2 or smoothing of V0 to P2. Okay, so I'm not an expert on this, as you might have already noticed, but let me kind of now give you the key setup and example, yeah, where in which I'm interested in. So I mean, maybe as a remark, in the one-dimensional case, so for curves, one could look at a family of conics where the general fiber would be projective line and the special fiber could be a degenerate conic. So in other words, yeah, something which is reducible and has two P1s that cross in the point. So that is then singular. And now we look at the same question in dimension 2. And the general fiber should be the projective plane. And in order to state how such families look like, or in particular, what kind of singular projective surfaces appear in this setting, I want to recall the notion of weighted projective planes. I imagine many of you will know this, but just in case. So please stay here. Okay. Recall, if we have integers A, B, C, positive integers, then the weighted projective plane PABC is defined to be, well, basically in the same way as we would define the projective plane P2. That's the case when all these weights are 1. We take A3, remove the origin, and now we identify points, I call them x0, x1, x2, is identified with lambda to the A x0, lambda to the B x1, and lambda to the C x2, where lambda is a non-zero scalar. Okay, so note there is also a different object that is sometimes called weighted projective plane, and that has a stacky nature. So that one would be a smooth thing, whereas this one is really a projective variety that's singular. And so this is known as weighted projective plane. And it has up to 3 singular points as so-called cyclic quotient singularities in the following, but kind of some of these singularities might actually be smooth points. For example, if all ABC are equal to 1, then we just get P2, which is smooth, so there are no singularities. Maybe the better phrase would be it can have cyclic quotient singularities in the following points. In P1, which is well, I want to denote, call this P1, and there the singularity is 1 over A B C. So what does this notation mean? This means we take a cyclic group of order A, and we act on the, so this is isomorphic as a group to Z modulo A, Z. And now we act on this, we act with this on A2 with weights B and C. So in other words, the matrix is something like epsilon to the B, epsilon to the C, where epsilon is an 8th primitive root of unity. So this is the singularities that we get. Then for the next point, which looks like this, we get 1 over B AC, if I'm not mistaken. And for the last point, just this form, we get 1 over C AB. So here we've got a cyclic group of order B acting. Here we've got a cyclic group of order C acting. And as soon as this weight A is bigger than 1, the point will actually be singular. Well, okay, I mean, typically I assume, that A, B, and C are co-prime. And I guess then the statement is, I mean, pairwise co-prime. Maybe that's what I want to say here as well. Pairwise co-prime. Okay, so these are very explicit, nice singular surfaces with up to 3 singular points. And now the theorem that tells us how all of these degenerations of P2 look like is the following, due to Hacking and Prohorov. It's again a very beautiful theorem. And it says this is from around 2005. And I should say it builds on earlier works of Badeshku from 1986 and Manetti from 1991. And actually the singular surfaces that appear as degenerations of P2 are also called Manetti surfaces, because he did a lot of work on that. So if W is a normal surface with only quotient singularities, so in principle here we would allow more general quotient singularities than just actions, quotient singularities coming from cyclic groups. So unfortunately this blackboard moves all the time. Let's see. Oh. Normal surface with only quotient singularities. Then the statement is that this W admits a smoothing to P2 as defined down here. If and only if W is a weighted, I leave some space here because it's not quite true what I'm saying. So you take weighted projective planes of this form A squared plus B squared plus C squared. And here A, B, and C is a Markov triple. So the first non-trivial example would be 1, 1, 4 on that weighted projective plane admits a smoothing to P2. And actually, yeah, all these weighted projective planes that come from Markov triples in this way admit a smoothing. But there are some more that are obtained from these guys by deforming and smoothing just some of the singularities. For example, we could smooth out just one of the singularities, not in an arbitrary way, but it needs to be a so-called Q Gorenstein smoothing of such a weighted projective plane. What does Q Gorenstein smoothing mean? If we have this family here, this V is a threefold, and we want this threefold to be Q-Gorenstein, and that means that the canonical class, if we multiply it with with some integer, we can turn it into a. I mean, so the canonical class is only a Weyl divisor here in general, and so by multiplying with an integer, we can make it a Cartier divisor. That means Q-Gorenstein. Okay, so this is the result of Hacking and Prochorov, and again, we have a geometric situation where the Markov tree plays an important role and gives some kind of parametrization of a geometric structure or situation. Okay, and so then
by Q-Gorenstein smoothing, you mean that W remains a singular, but Q-Gorenstein.
Say it again, please.
So, so what do you mean by Q-Gorenstein smoothing? Then, if W is a smoothing, then
yeah. Sorry, maybe I should call it partial. I mean, yeah, or I should call it. Sorry, yeah, you're completely right. I should call it Q-Gorenstein deformation.
I see. So the condition is that the threefold is Q-Gorenstein.
Yes.
Okay, thank you.
Yes, it's a deformation such that this threefold is Q-Gorenstein. Yes. Is that answering the question?
Yes, thank you.
Okay, thank you. Yeah, I agree. It was not quite ideally formulated. I mean, the point here is somehow that all the singular points, because of these squares, they are very special cyclic quotient singularities. They are so-called Wahl singularities. And these Wahl singularities, they always admit such a nice Q-Gorenstein smoothing. That's one thing that one needs to show, and for this one passes to some kind of to a so-called canonical cover of the singularity, which turns out to be a hypersurface singularity of type A, and then we deform this hypersurface singularity such that this deformation is equivariant with respect to this covering map. And so that will then induce a deformation of the original cyclic quotient singularity, this Wahl singularity. That's one part of the story. And the other part of the story is that one needs to show that these local deformations have no global obstruction. So there's a nice local to global behavior in this case. And this is part of what's behind this story, at least to go from this side to, I mean, that all of these things have such a smoothing, and then one needs to work in order to show the converse direction as well. But I don't want to go into this because my main point is the connection now of these two stories. So because they are kind of both parameterized by the Markov tree, one can wonder how they are related. And this is the following result. Okay. So the question that one can ask is there direct relation, whatever that should mean, between degenerations of P2 and vector bundles on P2. Okay. And an answer to this question is the following theorem due to Kawamata from 21. This builds on, I mean, what I'm stating now is a special case of this theorem. And it builds on earlier work of Hacking from 2013. So we start with the Markov triple A1, A2, A3. Let this be a Markov triple. And let X be the corresponding weighted projective plane. So now we know that this X admits a smoothing to P2. This is the result of Hacking-Prochorov that's up here. So the statement is here, there exists a smoothing to P2. Maybe, yeah, maybe that's okay. I mean, it's a bit subtle as far as I understand. One can in general not expect the family that comes from this theorem of Hacking-Prochorov to work directly, but potentially one needs to do kind of make this disk a bit smaller and do some base change in order for the to get the right family for this theorem here. So it's not necessarily the family that, I mean, that's kind of the starting point is this result of Hacking-Prochorov, and then one needs to modify it a little bit in order for this theorem here to become true. Okay, so there exists the smoothing, and then let's see, reflexive sheaves. F1, F2, F3. Wait. Ah, yeah. Okay. On X of ranks rank of Fi equal to Ai. Sorry, not no, it should be, yes. They are of rank Ai squared, sorry, where these are the weights from above, from the Markov triple that we fixed. And so these reflexive sheaves deform to vector bundles E1 up to direct sum A1. So we take A1 copies of a certain vector bundle E1, and same for A2 and E3. And so these vector bundles are on P2 now, such that E1, E2, E3 is a full exceptional sequence with ranks A1, A2, A3. Okay, so let's look at this. The starting point is this Markov triple. Then, given the Markov triple, we look at the corresponding weighted projective plane. Hacking Prokhorov tell us that there exists a smoothing to P2. Then we might need to modify this family a little bit. But after having done that, the statement is, I mean, this is about this deform, which I will kind of explain in a moment what I mean by that. There exists reflexive sheaves on our singular surface that deform to a full exceptional sequence up to multiplicities on P1. So that's the result of Gorodenzev-Rudakov, and that kind of now gives us a relation and kind of telling us actually, if we want to, we can think of all full exceptional sequences of P2 as coming from certain collections of reflexive sheaves on such weighted projective planes. So maybe to say what this deform should mean, here deform means that there exists a sheaf Fi tilde on the threefold V such that restricting this Fi tilde to the special fiber, to the singular fiber, gives us this Fi, and restricting Fi tilde to the smooth fiber sorry, this gives us AI times. So that's the statement, that one can actually lift these sheaves to the whole family, and then if we restrict it down to the general fiber, we get these exceptional ones. Okay, and these sheaves, they are almost exceptional objects in the following sense. So moreover, that all higher x vanish, this condition is satisfied. And also we have this, that morphisms only flow in that one direction. This condition is also satisfied. So x greater equal 0 from Fj to Fi is 0 for j bigger than I. So we only have morphisms from small to large. yeah, but what's not satisfied is that the endomorphism ring is minimal in general. So this is the following remark. I start here. Part A is that the K dimension of the endomorphism ring of Fi is AI squared. So Fi is exceptional object if and only if AI is equal to 1. And this is by what we've discussed here. This is the case if and only if Pi, the corresponding potentially singular point, Pi is a smooth point. Okay. And yeah, from my perspective, that's kind of the boring situation. And then part B of the remark. Okay. Says the following. These endomorphism algebras of these reflexive sheaves Fi. Maybe before I say something about this endomorphism algebra, I should say one can be more precise. So one of these sheaves will always be a vector bundle, no matter how, I mean, we can kind of choose it to be a vector bundle. So there is some kind of choice of ordering here involved as well. The other guys will be locally free everywhere except for the singular points. I mean, that's kind of a property of being reflexive. And in the singular points, they are either locally free as well, but what will also happen is that they are locally isomorphic to the to some of copies of the dualizing sheaf, and so that's what people sometimes call locally dual free or something like this. So this is kind of the worst thing that can happen, is that in one of the singular points, it's locally isomorphic to something like omega x to the direct sum rank, what's the rank, AI squared, something like this. Okay. Okay, so that's a comment on this, how these sheaves look like. And here, this endomorphism ring, this has been explicitly described. So it turns out that this, well, I mean, this statement here already says it's always a finite dimensional K algebra. It's almost never commutative, only in very kind of special situations it's commutative, but still it has a very nice structure from my perspective. It's local. All relations are monomial relations, so and it's a quotient of a free algebra in finitely many variables by a two-sided ideal that's generated by monomials. And yeah, the structure kind of, one can recover quite a few properties of the singularities from the structure of these algebras. And that was my motivation to study them so they are explicitly described in joint work with Joe Karmazin. From some years ago. And this description actually works for all cyclic quotient singularities of, yeah, kind of sum 1 over R 1 comma A. So a cyclic group of order R acting with weights 1A, and one can show that any cyclic quotient singularity in dimension 2 can be brought into this form. And so for those, we would call these algebras KRA with these two parameters. And yeah, I mean, here I should say for all two-dimensional, we're always in the two-dimensional setting here, cyclic quotient singularities. Yeah, it's non-commutative in general, but it's associative. And one kind of special case would be that that A is R minus 1. I mean, here also R and A, one can assume them to be coprime. And so then one family is the family where this twisting parameter is R minus 1. And this gives just then K R minus 1 is just Cx modulo x to the R. So that's commutative and R dimensional as should be. The other extreme case is that A is equal to 1. Then we get KR1 also commutative, C x1 up to xr minus 1 modulo x1 xr minus 1 squared. So this is something like a fat point, yeah. And this is the Gorenstein case. These are all the Gorenstein singularities. Have this, yeah, they are in this on this side, and this is some kind of Golod singularities. And apart from these two extreme cases, everything else is non-commutative. And yeah. If you are interested, you can look in the paper and see how this description looks like. It's kind of very close to the description of the commutative coordinate ring of the corresponding surface singularity. But then you kind of take, well, a non-commutative deformation of that. Okay, so now what do we do with these? Why did I introduce them? Well, these algebras turn up in the following theorem due to Karmazin, Kuznetsov, and Schinder, published in 22. And again, I'm only stating a very special case, or quite special case of this result. What does it say? So X should be a normal projective toric surface, then it follows that it only has cyclic quotient singularities, so only singularities of this type. Then we require that the Grothendieck group of X is free of finite rank T. So in general, we could have some torsion in there, but we need this assumption in order for the result to be true. For example, T would be equal to 3 if X is such a weighted projective plane. I pairwise co-prime. Then the statement is that bounded derived category of X has a decomposition into bounded derived categories R1, A1, mod. So these algebras are the algebras from before, these finite dimensional local algebras, and the whole derived category kind of decomposes into derived categories that are described by these finite dimensional, in general, non-commutative algebras. The T is the same as this T here, and yeah, morphisms, so these brackets mean this should be a so-called semi-orthogonal decomposition. In our situation, it's kind of a mild generalization of a full exceptional sequence. So these categories are subcategories in here in some way, and they generate this whole category. Morphisms only flow in this direction, say. This is the statement, and this X, so these R1, A1, so these T algebras that we have here correspond to T singular points. Some of them again might be smooth points, yeah, but it's up to, we have up to T singular points on this surface here. Okay, and so if we have a smooth point, then it actually just reduces to an exceptional object, and we would get, yeah, this is something I should have said before as well. In the special case that RT is equal to 1 or any of the other Ri, this algebra is just isomorphic to the ground field. Okay, and so then this category is generated by some exceptional object. But it's known that as soon as X is singular, we cannot expect all of these algebras to be just the ground field, because then this side would correspond to some kind of smooth category, and on that side we have a singular category, and so that cannot match up. As soon as X is singular, one of these algebras also needs to be non-trivial. Okay, so yeah, maybe these KRIAI are as below. And so in other words, the derived categories of these algebras can be seen as kind of fundamental building blocks of projective toric surfaces. And actually the result is more general than that. It deals with more general projective surfaces with only cyclic quotient singularities. And also this assumption here is only needed to make the theorem, to be able to state the theorem in an easy way. One can modify the statement to get rid of this assumption as well, which is also quite beautiful. But now I want to, in the last 4 minutes, say something very briefly about semi-orthogonal decompositions of singular varieties in higher dimensional examples. Let's see. So, okay. So higher dimensional varieties. So now, yeah, I'm interested in generalizing this result of Karmazin, Kuznetsov, Schinder to higher dimensional varieties. And one example that we have this is work in progress, is following. I mean, this is kind of the simplest version of the result. So take a higher dimensional weighted projective space of a very special form, just for simplicity. So here we have n, and here we have all the other weights are 1, and we have n times this weight 1. So this is an n-dimensional singular variety with a unique singular point and its Gorenstein. And the statement is that then the bounded derived category of X is equivalent to the bounded derived category of a finite dimensional algebra, which is the endomorphism algebra of some nice complex T. So we take the bounded derived category of finite dimensional modules over this finite dimensional algebra. T is a bounded complex. So it's an explicit bounded complex of vector bundles on X. And so one can make this endomorphism with some work. One can also make this whole endomorphism algebra explicit if one wants to. What we can make explicit, if we kind of decompose this derived category into smaller parts, splitting off some exceptional objects, then we get a big part that contains the singular information, and we get two smaller parts. So this is just generated by the structure sheaf. This is generated by O twisted by N, which by our assumptions here, this one is a line bundle actually, and it's also exceptional. So these two exceptional line bundles generate these two pieces, and the rest, the orthogonal to the category that they generate, is again described by a finite dimensional algebra Rn, and this we can describe explicitly. So Rn has this description. And what's interesting, I think, I mean, I'm already over time, so maybe I stop here, and if you're interested, we can talk about this in a moment. Okay, thank you very much, and sorry for going over time.